Hi guys, welcome back from spring break. Of course, this week is your week for doing tests and exercises and everything for lesson 2. So make sure you get your work in early enough where I can grade it and give you feedback, and you can apply that feedback and get better scores on your exercises and possibly do better on your test. A lot to do this week, just not that much time to do it. So let's get down and get it done. All right, this lecture, it's your last lecture for this lesson, and it's basically just a review of working some problems. Now, I asked you in the announcements to give me any problems you're having issues with, and nobody did. So I just pulled out a few random ones from your book, and I put them up here on my presentation, and we're just going to work through a couple from each section, and that's going to be the end of the lecture. So let's get on to it. Now, Chapter 4, it was all about series circuits. Now, series circuits, they've got 4 characteristics. First one is current is constant. Now, that's a rather important one because current being constant, that means it's the same in all the components. So all the components have got a common factor for you to work with. All right, second is the total resistance is equal to the sum of the individual resistors. Pretty straightforward there. Total voltage, doing Kirchhoff's voltage law. Kirchhoff's voltage law says the total voltage is equal to the sum of the individual IR drops, or voltage drops. So if I've got 3 resistors, each one is going to drop a specific voltage. The sum of those 3 voltage drops has got to equal the total supply voltage. Total power, well, just like voltage, you're going to have your individual voltage drops, which means each resistor is going to consume its own amount of energy or its own power. So the total power consumption is equal to the sum of the individual power consumption. Now that's fine and dandy, but how do we apply this stuff? Well, here we have a circuit. This circuit has 2 unknowns. We don't know the resistance of R2, and we don't know what our source voltage is. But we have all the information here that we need to figure out those 2 unknowns. Well, quickest and easiest in this situation is figuring out R2. Because what we do know is the value of 2 of the resistors, 120 ohms and 100 ohms. And we also know the total resistance. So finding the resistance is as easy as subtraction. You're going to subtract 220 ohms from 900 ohms. And that will give you your last value, of course. So R2 is going to be equal to 680 ohms. But what about our voltage source? Well, we've got half of Ohm's law right here. Ohm's law says that voltage is equal to current times resistance. In the case of a series circuit, total voltage is equal to current times total resistance. So how do I find current? Well, can't do it from R1 because it only gives you one piece of information. Can't do it from R2 because you only have one piece of information. So the resistor that gives me the most information is right here at R0. And it says it's 120 ohms, and its power consumption is 48 milliwatts. So how do we figure out from power and resistance what our current is? Because, of course, current is always the thing we'd be going for anyway. Well, we know that voltage at R0 is equal to the current times the resistance of R0. We also know that the power at R0 is equal to the current times the voltage at R0. Well, since I only have power and resistance to work with here, and my main objective is to come up with current, well, I want something that I'm going to want to be able to state power in terms of current and resistance. Well, just looking here, I've got to substitute my voltage at point 0, and I've got voltage at R0, and I've got an equivalent for the voltage at R0, so I can say the power at R0 is also equal to the current squared at R0 times the value of R0. So the current is going to equal the square root of the power at R0, over R0. And of course, square root over the whole thing there. So let's pull out the calculator. And the power at R0 is 48 milliamps, or pardon me, 48 milliwatts. There's 48 milliwatts divided by 120 ohms equals 0.0004. Now we take the square root of that. So my current at R0, or current in my circuit, or total current if you will, is equal to 20 milliamps. So now I've got my total resistance and my total current. So now I can just plug in Ohm's law. 20 milliamps times 900 ohms equals 18 volts. All right, now I've got some of the basic calculations taken care of here. If I was doing multiple problems with this diagram, say they wanted the power at R0 and R2 or whatever, I now have the ability to quickly plug these numbers back in anywhere I want. You know, referencing the basic equation and using the numbers I gain from this, I can use it as many times as I need to. So this is why on tests and stuff, not only do I demand that you document your work, but this is why you should want to be documenting your work, so you don't have to redo the same work over and over and over again. And then, of course, it's a good habit to get into for being a technician further down the road. All right, so this is your simple, straightforward series circuit. Now, another simple, straightforward series circuit is one like this, where I have a straight-on series, only one current path, but I've thrown in a ground reference point. And, of course, that ground reference point tells you where you're going to hook your negative lead anytime that reference point comes into play. So if I tell you measure from B to D, that reference point doesn't come into play at all. But if I tell you A to G, well, G is where your ground probe has to end up. If I say D to G, G is still where your ground probe has to end up from your meter. Now if I say D to G, my ground going there and my positive lead going there, remember, series circuits do have polarity for each resistance. And the polarity is, it is negative where the current enters, and it is positive where it exits. So in this case, I'm placing my negative probe, or my ground probe, onto the positive side. That means my reference point is going to be higher than my measurement point. And that is why you end up with a negative reading on your meter. So any reading I do, say D to G or C to G, is going to have a negative reading. The absolute value will not change. Okay, if I do the math, say from point A to G, that means I've got resistor 1 and resistor 2, R1 and R2, 120 ohms and 880 ohms. So that's going to be a 1 k ohm circuit. Of course, I have to figure out what my total resistance is before I can do anything, because I got no current, I got no power, but I'm given all the information to get current. And my total resistance, if you add up your resistors, is going to equal 1.8 k ohms, or 1800 ohms. So let's real quick figure out what our current is. So that is 36 volts divided by 1800 ohms, or 20 milliamps again. So measuring from point A to G, it is essentially a 1 k ohm resistor times 20 milliamps. Well, I do believe that's going to be a 20 volt. A 20 volt measurement, or a 20 volt voltage drop. Now let's say we go D to G. Well, I've got 330 ohms plus 470 ohms, so that looks like about an 800 ohm resistor. And 20 milliamps times 800 ohms, well, that's going to get you about 16 volt voltage drop. However, if I'm taking and measuring on my meter is going to measure a negative 16. Once again, the absolute value remains 16 volts, but its polarity for our measurement is going to be seen as a negative 16. And just to add up, we had a 1K and an 1800 or an 800 ohm. That gives us a total resistance of 1.8 k ohms. And then we had a 20 volt voltage drop and a 16 volt voltage drop. Well, that equaled out to 36 volts. So everything is checking okay. And once again, I've got the information I need to work multiple questions concerning this diagram. Okay, total resistance, common current, the voltage, and then the individual resistors. So it's documented. I can go back and use it over and over and over again. All right. From Chapter 4, we went into Chapter 5, and Chapter 5 was all about parallel circuits. And parallel circuits also have 4 characteristics. Might help if I actually numbered them right. First characteristic, voltage is constant. Because, of course, in a parallel circuit, they're all connected across the same source. Hence why they're in parallel. So voltage is constant. Current is the sum of the individual branch currents. The equivalent resistance. Don't forget, when we're working on parallel circuits, our objective is to reduce it down to the simplest form. So as if it was a single series resistor. Which is why this is called resistance equivalence instead of total resistance, because it is the equivalent of a single resistor across your power source. So your equivalent resistance is equal to the inverse sum of the individual branch current, or branch resistance. Or the total conductance is equal to the sum of the individual branch conductances. And I find it much easier to work parallel circuits in terms of conductance than I do in terms of resistance and all the inverses and all that stuff. And of course, power, the total power, is the sum of the individual branch power consumptions. So, here's a basic circuit. I've got two resistors in parallel. And when working with two resistances, we can do calculations either using the conductance method or using the special MAD method, where you multiply, add, and then divide. So M-A-D, MAD. So using that method, I'd have 120 ohms times 60 ohms over 120 ohms plus 60 ohms. Let's see, I'm not going to do the 12 times 6 in my head here. So 7,200. 7,200 over 180. Which equals equivalent resistance of 40 ohms. Now remember, one of the characteristics that I did not point out for the resistance side, and let me back up to that, the equivalent resistance is going to equal the inverse sum, or the sum of the branch conductance, and it will always be less than the lowest resistor in the circuit. So in the circuit, I had my lowest of a 60 ohm, and we can see the equivalent resistance is 40 ohms. Now, let's take it with the inverse sum, which means we're going to take 1 over R0 plus 1 over R1. Which is the same as taking the conductance of the two resistors. So the total conductance for the circuit is going to equal 120 ohms, 1 over X, plus 60 ohms, 1 over X, the reciprocal. And then we get the total. And then we go 1 over X, because that's what we end up with there. We'll go 1 over X again. So 0.025 Siemens. That is the total conductance for the circuit. But we know conductance is the reciprocal of resistance. So we'll take the reciprocal of 0.025, and that comes up to 40 ohms. So MAD method or inverse sum of the reciprocals. Now, this method I can use on a circuit no matter how many resistors there are. The MAD method only works for 2 resistors. So this tends to be the one I lean toward. Okay, but you don't always have all the information there. In this case, I've got a total voltage, so 120 volts, and you'll notice they're all tied across the same voltage buses. So I've got 120 volts across every resistor. I should say across every branch. Each one of these is known as a branch. Alright, so that's branch 1, branch 2, branch 3, and branch 4. And each one of these branches has got 120 volts across it. Now, in this case, I know what my total current is. I got 160 milliamps total current. So I have 8 milliamps in branch 1, 12 milliamps in branch 2. Don't know what branch 3 is, but I got 60 milliamps on branch 4. So I've got a total right there of 80 milliamps. Well, let's branch 3. Well, we know total current equals the sum of the branch currents. That's not a very good looking sum sign, but you get the idea. So 160 milliamps minus 80 milliamps. Looks like this guy's got to be 80 milliamps. From this information, we can now figure out what R0 is, what R1 is, what R2 is, just using Ohm's law. Because branch resistance is going to equal volts times branch current. So 120 volts times 80 milliamps, 8 milliamps, 0.008 times 120 equals, times 120, pardon me, 120 divided by 8 milliamps, that's volts over branch current, stupid me, equals 15 kiloohms. Same with branch 2, 120 volts divided by 12 milliamps equals 10 k ohms. Clear? Let's see. I've got 80 milliamps, 120 divided by 80 milliamps equals 1500 ohms, or 1.5 k ohms. And finally, 120 divided by 0.06, 60 milliamps, equals 2 k ohms. Now you notice the larger or the smaller resistors draw the most current. The old saying, something is going to take the path of least resistance. Well, current takes the path of least resistance. So the lower the resistance, the higher the current. Now what happens if we add another resistor in here? I don't know what just happened again. There we go. Okay, if we add another resistor in here, nothing's going to change for each branch because each branch still has its same resistor and still has the same voltage going through it. So all we're going to do is add another resistor, which is going to add another path for current to flow. Which means we add another resistor, we're going to increase the current. Well, if we increase the current and we have a constant voltage, then the resistance of the circuit has to go down. That's Ohm's law. Okay? For a constant voltage, if your current goes up, then your equivalent resistance has got to drop. That's just the way it works. So, something to remember. Now, we've got the total current and we've got the total voltage, so we can easily figure out what the equivalent resistance of this circuit is. So we're going to do it two ways. We're going to use the total Ohm's law method, where our equivalent for the circuit is going to equal total voltage over total current. Remember, total is different than individual branch as you're writing it down. A lot of people make that mistake where they're talking about an individual, or they're talking about a total, but they calculate off of an individual branch, and they get all kinds of hosed up that way. So total voltage is 120 volts. Total current is 160 milliamps. Exponent NS3, that way. There we go. So my equivalent resistance is going to be 750 ohms. So that was 120 volts. That was 160 milliamps, which equals 750 ohms. Now we're going to go ahead and do the conductance method. So I'm going to calculate the conductance or the total conductance of the circuit, which is going to equal 15,000 1 over x plus 10,000 1 over x plus 1,500 1 over x plus 2,000 1 over x equals 0.0013333333. Go 1 over x on that, and I get 750 ohms. So I can quickly double check my figures, and they come up properly twice. So there you go. There you go. Multiple branches, very little information given, but enough. I've got enough with the voltage and the current at each branch, and then the total current, that I'm able to calculate any characteristic of this circuit that I want. Alright, I threw this slide in again because I was going to do exactly what we just did and calculate multiple ways. So I'll just keep on going on past that. Alright, chapter 6 is where it all came together, where we had to evaluate circuits that had elements of series and parallel, and we had to figure out if they were parallel circuits in series or series circuits in parallel. And this is a good overall example right here. In this case, we have multiple paths, so we have to figure out, okay, am I ending up with multiple parallel in series, or do I have a couple of resistors in series in parallel? So when you're looking at a figure like this, it's best to kind of go along your current path. And you see this first one, I break out into two current paths. So I'm just going to draw it as a line graph, and let me move my my pen stroke out of the way there. So I'm going to draw it as a straight line graph kind of thing. So up here, I've got R0. And down here on this path, I've got R1. And R0 goes straight back to the positive side. Remember, the big bar is positive, the little bar is negative on your voltage source. Exiting R1, I go into another split. And on this split, I've got R5. And down here, I've got R2, R3, and R4 in series. All right, and this branch is coming back together on the other side of R5. And when they come together, they go through R6. See, the two branches meet up together, and there's R6 in series with them. But at the output of R6, I end up joined back up to R0. So what I have is a parallel circuit that happens to have the elements of series. Okay, R1 is in series with this network of R2, R3, R4, and R5, which is also in series with R6. So between this point and this point, I've got my total overall voltage. Between this point and this point, I've got the overall voltage minus the voltage drop across R1 and the voltage drop across R6. My total current is going to branch off across there, and then the remainder is going to go through here. So I've got the same current at R1 and R6 and completely across these two branches. However, that current once again will get divided between the two current paths. So I'll have the total current minus the drop across R5. That's what the current will be across R2 and 3, but R2 and 3 will share the same current. So first thing I want to do is collapse this one to its equivalent, then take the set of series resistors here and collapse them down to a single value, so I can then collapse R0 and this mess down to its equivalent value. Once I do that, I can calculate my current and different voltage drops, and I can start expanding out to work across the circuit. So to do that, I'm going to need another slide. Let's see, have I got another slide set up? No, I don't. But I do now. So now let me redraw that circuit real quick. And go back and get my values. Let's see here. I had a 1K and a 15K. Let's see here. 15, 1, and 5. One, two, three, four, 5. 1, 2, 3, 4, 5, 6, 7. Oh, okay. That's right. Messed up. And come back to this again. Okay, R5 is 10, R2 is 5. Let's see. R3 is 15, R4 is 10. R5, R6, 5, 7, 1, 2, 3, 4, 5, 6, 7. Good. So R6 is 1.5K. So 1, 2, 3, 4, 5. Oh, that's R0. That's R1. 2, 3, 4, 5, 6. There we go. And V equals 36 volts. All right, now we can get to real work here. First off, I've got 15K and 30K. All right, my series circuit here between R2 and R4 is 25K and 5K. That's 30K. And 10K ohms. I could use the MAD method, but instead I'm going to use the inverse reciprocal method, or the conductance method. 30K 1 over X plus 10K 1 over X equals 1 over X. I got an equivalent resistance of 7,500 ohms. $7.5K ohms. Okay, that's 7.5K ohms plus 1K and 1.5K. That's going to bring me up to 10K ohms. So that is that equivalent at 7.5K ohms. Finishing out the series circuit, plus R0 plus R6 equals 10K ohms. So this entire mashup there is equivalent of 10K ohms. So now I've got just two parallel branches, one at 10k ohms, one at 15k ohms. So we'll go ahead and do it again with using the reciprocal method, or the inverse reciprocal method, or the method of conductance. So 15k, take the reciprocal, plus 10k, take the reciprocal, add those two together. Now take the reciprocal of that to convert from conductance to resistance. The equivalent of this circuit equals 6k ohms. So the total current for this whole circuit is 36 volts over 6k. Divided by 6,000 equals 6 milliamps. And I'm getting off to the side of my my pad there. So let me move this over just a little bit. That'll help me out. There we go. All right, so my total current for this whole circuit is 6 milliamps. From this point to this point, I got 36 volts. So 36 volts divided by 15k for the first branch. 36 divided by 15k equals 2.4 milliamps. Which is going to leave me 3.6 milliamps for this side. So from there to there, I'm dropping 3.6 milliamps. And just to be sure, we're going to go, well, it's quite obvious because 36 volts divided by 10k, that's going to be 3.6 milliamps. But I'm going to do the math anyway. 3.6 milliamps. Amazing. All right, now I can continue expanding out again. So 3.6 milliamps across this whole circuit. So that's going to be 3.6. That's going to be 3.6 milliamps. And then we're going to split across. However, this is equivalent to 7.5k ohms. So if I use Ohm's law, 3.6 milliamps times 7.5k, 3.6 exponent minus 3 equals times 7,500 equals. So there's going to be a 27 volt drop across this section here, leaving 9 volts across the 1.5 ohm and the 1k, or 1.5k and the 1k. And just to be sure, 1,000 times .0036 equals 3.6 volts. And 1500, oops, not 15,000, 1500 times .0036 equals 5.4 volts. So those are individual voltage drops across the 1K and the 1.5K. And I know I've got 27 volts across this network here. So the 10K ohm resistor has got 27 volts across it. So what is the what's the current at that 10K ohm? Well, I think it's going to be like, I don't know, 2.7 milliamps. 10,000 1 over x times 27 equals 2.7 milliamps. Okay, 2.7 milliamps minus, or 3.6 milliamps minus 2.7 milliamps is going to equal 9 milliamps is going to be consumed by this side. And then we can compare that, multiply each of these resistors, and they should equal 27 volts. So let's go ahead and do that. 9 milliamps times 5K equals 4.5 volts. Did I say 4.5? Yes, I did. Okay. VR3 is going to equal 9 milliamps times 15K. Oops. What did I say? 3.6 milliamps. 2.7 milliamps minus 2.7 equals 0.9 milliamps. 0.9 milliamps, not 9 milliamps. 0.9 milliamps times 15,000 equals, whoops, 0.0009 times 15, 1, 2, 3, equals 13.5 volts. I'm writing out of space again. And VR4 is going to equal 10K to 3 times 0.0009 equals 9 volts. Okay, so 13.5 and 13.5 looks like that equals 27 volts to me. So we've pretty well expanded as far as we can expand. But you saw that we had to make use first of properties of series, then parallel. Okay, first property of series, the sum of the resistances, then parallel to get the equivalent for that circuit. Then the property of series again, sum of the resistances to get that side. then back to parallel to get the total equivalent resistance. Once we had that, we could calculate the total current for the entire circuit, and then we could start expanding back out. We were able to figure out how much current that branch was going to use. Once we knew that, we knew what the branch current had to be for this branch. And then we were able to start expanding back out on this side. Until finally we ended up using properties of series to get the voltage drops across those three resistors. You have to take your time. You can't get in a rush. And you have to look at what you're doing through the whole setup. Now, the last problem we're going to talk about tonight is out of your discussion questions. This is Lesson 2, Discussion Question 4. And basically, we had to find out the equivalent of this circuit when this potentiometer was set all the way up, all the way down, and dead center. Because when it was set up all the way up, our series circuit here changed. You can see this is a series parallel. That is to say, it starts out by splitting paths, but it finally ends up with a single path going back to the power source, to the positive side of the power source. And that's pretty much how you identify whether you've got a series parallel going on or a parallel series going on, by the fact that a series parallel will end up with either leading with a single component and the output of that component splitting into many paths, or many paths coming back into a single component. Those are the main indicators of a series parallel. Whereas a parallel series starts out with many paths and ends up with many paths coming back into the main trunk. So that's what you're looking for. You either got a resistor in the way of the main trunk or on the input from the main trunk, or you got many paths leading to the main trunk with no other component in the way. All right. So with the resistor tuned all the way to the top here, this 5K R2 is then straight in series completely with this R3, giving us a 15K branch there to go along with the 15K branch over here. With it set at the bottom, this branch is 10K in series with now an 8.3K, because this resistor and this resistor are completely in series, and your parallel just consists of these two. With it centered, half of R2 is in your parallel network, and the other half of R2 is in series with R1. So let's see how this works with R2 come on, work. There you go. With R2 maxed out. So with R2 maxed out, this branch consists of R2 and R3, and this branch R4. So this branch is equal to 15K ohms, and this branch is equal to 15K ohms, and we have a special case. If you'll recall, the special case of a parallel network of all like resistors, the equivalent resistance is equal to the value of one resistor divided by the number of resistors. So in this case, it's 15K divided by 2 resistors, or 7.5K ohms. Well, R1 still remains 3.3K. So 7.5K plus 3.3K, the equivalent resistance for this entire circuit, or the total resistance, since it's series, is 10K ohms. So 36 volts divided by 10K ohms, we're going to end up with 3.6 milliamps. Case A. 3.6 milliamps. Total current. My voltage drop across R1 is going to be the total current because it is a series circuit. .0036 times 3.3K equals 11.88 volts is your voltage drop across here. Now we can either just subtract from the 36 volts, or we can use our equivalent resistance times the current, which is what I choose to do anyway. So 7.5K times 3.6 milliamps equals 27 volts. 27 easy, even? And did I do that quite right? Sure doesn't look like I did it right, does it? Alright, let's see here. 10K ohms, 1 over X times 36 equals 3.6 milliamps times 3300 equals 11.88 volts. 0.0036 times 7500 equals 27 volts. Doesn't look like it's adding up to me. Does it to you? 5K ohms, 10K ohms, 15K ohms. R4 is 15K ohms. 15K and 15K, 7.5K ohms. Makes sense. Oh, what am I looking? I said 10K ohms. Nobody even caught me on that. That was incorrect. 10.8K. 7.5, 3.3, 10.8K. Not 10K. So let's redo this again, shall we? I think so. 36 divided by 10,800 ohms equals 3.333333 milliamps. And I'm going to go out 3 more decimal places there. Now, multiply that by 3.3K equals 11 volts. Times 7500 equals 25 volts. That's better. Okay, 11 volts and 25 volts equals 36 volts, so I know I'm doing something good so far. Since I'm dropping 25 volts From there to there, I have 25 volts on this branch, I have 25 volts on this branch, and since the branches are of the same value, I can quickly calculate the current for each, and of course just splitting the 25, so that's going to be 12.5 12.5, what am I thinking? 25 volts divided by equals 1.67 milliamps on each side. And then my voltage drop across R2 will be 5,000 times 0.00167, which is going to equal 8.35 volts. And should be able to double that for the 0.00167 times 10,000 equals 16.7, which pretty well looks like 25 volts to me. So we pretty well solved for everything on this with the potentiometer completely maxed out. So 3.33 milliamps. And then we can solve for each resistor once we have that current. Whoops. Okay, condition B. With the pot set to minimum. Darn it. Come on. Get to work. There we go. And for some reason my pen has quit working again. Okay, where was I? I do believe we were going to condition B with the R2 pot set to minimum. Well, that changes things because now we have a series circuit consisting of R1 and R2 in series with a parallel circuit consisting of R3 and R4. So this part, the series portion, is going to be 5K plus 8.8 there, plus 5K plus 3.3, which is going to be 8.3K. And then I've got the network down here that's 10K and 15K, so I know this is going to be less than 10K ohms. So 10,000, 1 over X, plus 15,000, 1 over X, equals, okay, so there is my total conductance. Now I'm going to invert it again, or take the reciprocal to get the total resistance, or the equivalent resistance. So in this case, my equivalent resistance is 6K ohms. Now my total resistance, since it's a series circuit, is going to be 14.3K ohms. So 36 volts divided by 14.3K. Or 14,300 equals 2.517 or 2.52 milliamps. So condition B, 2.52 milliamps. So once again, R1 is going to be 2.52. R2 is going to be 2.52 milliamps. R3 and R4 are going to split that, proportionally split that 2.52 milliamps. And the voltage across my parallel network here is going to be 36 volts minus the voltage drop across R2 and R1. Or I could just calculate the equivalent resistance times the 2.52 milliamps, which is what I'm going to do. Times 6,123 equals 0.000, oops, pardon me, 0.00252 times 6,000 equals 15.12 volts. So there's my voltage across my parallel network. My voltage drop at R2, real simple, 0.00252, clear, 0.00252, there we go, times 5,000 equals 12.6 volts. And 3.3 equals 8.32. Okay, if I add all those up, so 27.72, 27.7 plus 8.3, that looks like about 36 volts to me, so I know I've got my voltage drops right. Now I know I've got to split 2.52 milliamps across these two guys. I've got my voltage going across, so it's pretty easy to calculate at that point. 10,000, take the reciprocal, multiply by the voltage. So 1.5 milliamps on this side. Looks like I'm going to have about 1 milliamp on this side. So 15.12 divided by 15,000 equals about 1 milliamp. So that's how it works for setting on the side. You can get the idea from here. If I set it to the middle, I'm not going to work this one out. Or maybe I will. After all, this is recorded. You can shut it off anytime you want. Okay. So half of R2, 2.5, oops. 2.5 k ohms there, 2.5 k ohms there. So R1, half of R2, this side is going to equal 5.8 K. This half I'm going to have 12.5 K on this branch. Well, I've still got 15 K on this branch. I know that my R equivalent is going to be less than 12.5 K. So once again, let's just quickly work that out. 12,500. 1 over x plus 15,000. 1 over x equals 0.000147. 1 over x about 6818.2K, or 6.18 6.818 K ohms is about our equivalent there, which means plus 5,800 equals 12 K ohms for a total equivalent, or total resistance. Take the reciprocal of that, multiply times the voltage. So about 2.9. That's rounding up, of course. About 2.9 milliamps. And you get the idea how to calculate it out from there. So you can see how a potentiometer can vary the overall characteristics of a circuit with a given load. Now, this is the same sort of thing you get when, say, you've got a speaker circuit and you've got a volume knob. By varying the volume or the output, you're changing the characteristic of the whole circuit just to get your musical notes out your stereo system. All right, that's all I've got. With luck, you were able to keep up on this one. If you got any question about anything that I've done here, please contact me. Don't sit and wait and stew and pound your head. If you're out of the country, figure out a time that you can be available, your time, and then let's work it out that I'll make myself available to you, your time. Even during the workday, at times I can slip off to the side and take care of stuff like this. So don't be afraid to contact me. Other than that, don't forget, everything is due this week. Don't forget that part. Your lesson 2 test, all your lesson 2 exercises, all your discussion questions. You get the discussion questions into me by Sunday, and I'll give you credit for everything on your discussions, even if you've missed. Just get them done and get them in to see me. There's only 4 of you in the class, so that's a lot easier on me. Other than that, I'll see you in the funny papers, and I'll be starting lecture 7, or lesson 3, chapter 7, next Monday. Talk to you later. Oh, and I am in the office on Wednesday this week. Don't forget. That's 7 to 9 p.m. Central Standard Time. So I'll see you then. Bye.